So our topic now, which we'll be going to do in this particular session, is Nernst equation. So what is Nernst equation and what is the importance of Nernst equation in electrochemistry? Try to understand. The value of EMF of a cell or a cell potential can be easily calculated with the help of electrochemical series by knowing the electrode potential value, which is actually with reference to a reference electrode, that is the standard hydrogen electrode. And all those values of electrochemical series or the reduction potential which you get in electrochemical series is nothing but is calculated on or in standard conditions. When we say standard condition in electrochemistry, what do we mean is it's 298 Kelvin, it's 1 molar concentration, and if gas is present, it's 1 bar pressure. Now the big question is, if such condition does not exist, or if such condition is not there, let's say, if the concentration is not 1 molar, if the concentration is 2 molar or 0.5 or 0.01 or 0.001, if the temperature is not 298 and if the temperature is 300, how do we get the cell potential value? So that cell potential value is calculated with the help of Nernst equation. So the significance of Nernst equation is it helps us to calculate the value of cell potential or electrode potential in condition other than the standard states. So in standard state, we can easily calculate with the help of the values which we get from electrochemical series. But if the condition are not standard, then we take the help of Nernst equation to calculate the value. So the question is, how do we do it? So let us just try to see that. Significance of Nernst equation. The electrode potential of an electrolyte is said to be standard electrode potential if it is measured under standard condition. That is, the electrolytic concentration is 1 molar and temperature is 298 Kelvin. Okay, so that is what we call a standard condition in electrochemistry. Now, however, if the electrolyte concentration is different from 1 molar or the temperature is different from 298 Kelvin, what will happen in such cases? The electrode potential has a different value. So in such cases, what do we do is we use Nernst equation. Okay, now what is this Nernst equation? So that is what we'll be trying to find out next. So Nernst equation for electrode potential. Okay, so first let us try to find out the Nernst equation for electrode potential. Okay, the potential of an electrode at which the reaction, okay, so the reaction is this. We are taking a reduction reaction where Mn plus is the ion in aqueous solution. Okay, that is the electrolyte, and it is taking n number of electron to give you M metal, which is a solid. Take place is described by the equation. So this is your Nernst equation. So E Mn plus M, okay, the electrode potential of this particular electrode reaction will be equal to E naught. See, when we write E naught, that means it is standard electrode potential, which we get from the electrochemical series, minus RT by NF Ln M by Mn plus. So basically it is product by that of reactant, and enclosed in third bracket, it means that it is molar concentration, molarity. Okay, now this can be written in another way, which will be Mn plus M will be equal to E naught Mn plus by M minus 2.303. Now, I hope you understand Ln basically means log base E. So when log base E, we convert to log base 10, we multiply with a factor of 2.303. So this is natural logarithm log base 10 RT by NF log of MS by Mn plus. Okay, so this is nothing but your Nernst equation. So the above equation is called Nernst equation for electrode potential. Okay, where Em n plus M is nothing but the potential of the electrode at given concentration. Okay, see, that's why we are not using that particular symbol over here, not whenever we write it is in standard cases. So we know that it is not in standard cases at a given concentration. The concentration is not standard concentration. So that's why we are not writing any naught. E naught Mn plus M is nothing but standard electrode potential, which we know, which we get it from the electrochemical series, which will be provided. R is the universal gas constant. T is the temperature on absolute scale. When we say absolute scale, it means in Kelvin scale. N is the number of electrons involved in the electrode reaction. Now, how much is this N value? Now, what is the value of this N? That is nothing but this N, and F is nothing but 1 Faraday. That is 96,500 coulomb. Okay, by putting these values, we can easily find the electrode potential. The concentration of pure metal Ms, okay, whenever there is pure metal, remember that in any electrode reaction or cell reaction, the concentration of pure metal is always taken to be unity. Okay, so always remember that the concentration of pure metal is always taken as unity. Okay, so if we take it as unity, so what will happen is, so the Nernst equation is written as, so that metal concentration will become 1. Okay, so E n m n plus by m will be equal to E naught m n plus slash m minus 2.303 RT NF log of 1 by mn plus. Okay, why we are writing 1? Because the concentration of pure metals, okay, is always taken to be unity in electrochemistry. Then at 298 Kelvin, okay, let's say if the temperature is 298, let's say if only the concentration is varying, not the temperature. So if the temperature is standard temperature only at 298, what we can do is we can easily put this value, because temperature, if it will be 298 Kelvin, 2.303, R is fixed value, which is 8.314 joule per Kelvin per mole. That is the gas constant. N we don't know, but F is constant. F is 96,500. So we know the value of 2.303. We know the value of R as 8.314. Temperature is 298 if we are fixing it, if temperature is provided as 298 Kelvin, and F is 96,500. So if I put this value and simplify this, what I'll get is I'll get 0.0591, which is another form of Nernst equation. So remember that this Nernst equation you can use when they mention that the temperature is 298 Kelvin. So if they mention that the temperature is 298 Kelvin, you can use this form of Nernst equation instead of using the previous one. Okay, so remember that this equation, this last equation, is at 298 Kelvin, and this equation which you can see above is the equation at any other temperature than 298, so that you can easily put it. So if the value is 298, you need not put it, you can usually actually directly use this. Okay, so these are the two forms of Nernst equation for electrode potential when they have supplied you half reaction. Now, Nernst equation for cell EMF. Okay, how to find out for a cell, for a complete reaction. So for a cell in which a net cell reaction involving n electron is this. Let's say if the reaction taking place is this, A plus B of B will give you C of C plus D of D. Okay, that means A moles of A will react with B moles of B to give you C moles of C and D moles of D. How to write Nernst equation for this? It is again in the very same way. So we will write E cell instead of E and the expression of that particular reduction reaction. So it is E cell now. So it is for the full reaction. E naught cell. Okay, how to calculate E naught cell? We know now, E cathode minus E anode minus RT by NF ln. Then it is again concentration of product by that of reactant. So concentration of product by that of reactant. And remember that if there is any stoichiometric coefficient, basically what do we call as number of moles, then we raise it to the power. Okay, so you can easily see concentration of C to the power C, concentration of D to the power D, concentration of A to the power A, and concentration of B to the power B. Okay, Now, what we can write is E cell will be equal to E naught cell minus, again, that ln we can convert to log by multiplying by 2.303 RT by NF, again log, and again the expression remains the same, C to the power C, D to the power D by A to the power A and B to the power B. Now, the same expression we can write at 298 Kelvin again. So if the temperature is 298, we can put the value of R, we can put the value of F, we can put the value 2.303, we can multiply this, divide by 96,500, again you will get 0.0591. So these are the two expressions. So the last expression is at 298 Kelvin, and the previous expression before that, the above expression, is nothing but the expression at the other temperature other than 298. So these are the two forms of Nernst equation which we have to know. The previous one is for electrode potential. This is for the cell potential. Okay. Now, Nernst equation can be related with equilibrium constant also. So let us take the same reaction again. Okay. For a cell reaction having such type of reaction, or for a cell having a net cell reaction of this type, A plus B will give you C of C plus D of D. The Nernst equation is, how we can write the Nernst equation? E cell will be equal to E naught cell minus RT. Okay. Then ln or log, then you can write C to the power C, D to the power D, A to the power A, and B to the power B. That is what is Nernst equation, what we have learned. Now the question is, what will happen in equilibrium? I hope all of us understand what is equilibrium is all about. Equilibrium is a stage, okay, where the two reverse process of a particular system is taking place at the same pace or at the same rate. As a result, there will be no net change taking place in this system. That is what we call as equilibrium. So remember that at equilibrium, there is no net gain, no net work done in the system. Okay. So as a result, if our cell, okay, if our electrochemical cell is at equilibrium, okay, so what will happen is that system will not do any useful work. So basically what do we mean is that the system will not produce any EMF. Okay. So if the EMF will be not produced, or there will be no EMF, that means E cell is 0. Okay. So if E cell is 0, so at equilibrium, now what do we know? At equilibrium, the ratio of product by reactant is always known as equilibrium constant. Okay. So what is equilibrium constant? Equilibrium constant is nothing but the ratio of the equilibrium concentration of the product to that of the reactant raised to the power of the stoichiometric coefficient. That is what we have learned from the very basics, what we have learned in equilibrium in class 11. So whenever anyone say what is equilibrium constant, it is nothing but the ratio of the equilibrium concentration of the product to that of the reactant, and each of them raised to the power of the stoichiometric coefficient, or in simple words, number of moles. So you can clearly see that is your equilibrium constant, which is nothing but matching with our Nernst equation. So what do we do? If I put the value, what I'll get is E cell will be equal to 0, and C to the power C, D to the power D, A to the power A, and B to the power B becomes Kc. So if I put this as Kc and put E cell is equal to 0, so if I simplify that, what I'll get is E naught cell will be equal to 2.303, just converting ln to log NF RT log of Kc. So instead of writing C to the power C, D to the power D by A to the power A and B to the power B, what we can write is log Kc. And what we know is if the temperature is 298 Kelvin, so instead of writing R, T, and F, we can put the value, and what we can get is 0.0591 by N log of Kc. So the above expression is expression at other temperature, and the last expression is the temperature at 298 Kelvin. So depending upon the problem, we use the equation which we want. Okay, so that is the relationship between Nernst equation and equilibrium constant. Now, the relationship between cell potential and Gibbs free energy. So now the question is, what is Gibbs free energy and how it is related to cell potential? Now, if we understand what is free energy, or if we try to understand what is Gibbs free energy, it is nothing but the energy contained in a system or present in a system which is available to do some useful work. Okay, if a system has some energy which it can use to do some useful work, that particular energy is nothing but Gibbs free energy. So now try to understand the system. What we are talking about is nothing but a cell. A cell is nothing but performing a work, and by doing that work it is producing electrical energy. So our system, that is an electrochemical cell, is producing electrical energy by doing some electrical work done. Okay, so the electrical work, basically what we mean by electrical energy, is equal to the product. I hope from the basic of physics what you have learned, that the electrical work or the electrical energy produced is nothing but EMF. It's the product of EMF and electric charge that flows through the external circuit. That is how we get electrical work or electrical energy. So electrical work done is nothing but quantity of electricity flowing into EMF. Okay, which will be equal to NF into E cell. Okay, I hope you can understand quantity of electricity flowing, how much charge is flowing, how much we know that if 1 mole of charge will flow, it will known as 1 Faraday. Now we don't know how much charge is flowing in the circuit. So if it is N moles of electron flowing into the circuit, it will be N Faraday. So since we don't know how many number of electrons or how many moles of electron is flowing in the circuit, so we are generally writing as N Faraday. And what is EMF? EMF is nothing but E cell. So what is electrical work done? It is nothing but NF E cell. Now, according to thermodynamics, the free energy change is equal to electrical work done. Is it not? According to thermodynamics, according to the first law of thermodynamics, what do we know? Energy can neither be created nor be destroyed. So what we are saying is whatever the work done is actually is in the expense of Gibbs free energy, okay, or is in the expense of free energy or the energy which the system has. So that means whatever is the free energy change, whatever is the energy is changing for that particular cell, whatever is the free energy changing, that must be exactly equal to how much work is done. How much energy is lost is equal to how much energy is produced, right? Energy can only be transformed, it cannot be destroyed or it cannot be created. So if some amount of Gibbs free energy we are actually is changing of our system, that means the same amount of energy or the same amount of work done is also done in the system or is also produced in the system. So we know that some amount of Gibbs free energy is changing. How much is changing is delta G. So the same amount of work is done, and that work is nothing but NFE cell. So that means whatever free energy is changing is equal to NFE cell. So delta G is equal to NFE cell. And why we are putting minus? Because your Gibbs free energy in the process is decreasing. When Gibbs free energy will decrease, when that energy you will use, then only you can produce electrical energy. So some amount of energy has to be used, then only another form of energy can be produced. So some energy has to decrease, then the another energy will increase. So in our case, the Gibbs free energy of the system, that is your electrochemical cell, is decreasing. And how much it is decreasing? The same amount is increasing in the form of electrical work done or in the form of electrical energy, which is nothing but NFE cell. And we put a minus sign, which shows that the Gibbs free energy in the whole process is decreasing, it is negative. Okay, so that is the expression of delta G, that is nothing but equal to minus NFE cell. Now in standard condition, okay, if it is 1 molar condition or if it is 298, okay, and if it is gas, if it is 1 bar, then we write this expression delta G naught. Okay, so that is in standard condition will be equal to minus NFE naught cell. So this is what actually you need to understand about Nernst equation and how do we understand the relationship between Nernst equation and the equilibrium constant, Nernst equation and the concentration of the product to that of the reactant. So how do we understand all this concept is in this way. Okay, so that is how actually we can understand what is Nernst equation and what is the importance of Nernst equation.